Simply supported timber beams. A simply supported beam is one that rests on two supports and is free to move horizontally. Furthermore, the values of shearing force and bending moment will usually vary along a beam, which means you have two supports and typically you have a hinge and another support, a ruler. And the simply supported beam is one of the most simple structures. It features only two supports, one at each end. So this is an example of a wood or timber beam with a simply supported beam, which is at A we have a support and at point B as another support, and the forces along the line AB. And what is bending stress? Bending stress is the normal stress that an object encounters when it is subjected to a large load at a particular point that causes the object to bend and become fatigued. Bending stress occurs when operating industrial equipment and in concrete and metallic structures when they are subjected to a tensile load. And here's the formula for bending stress. We have a beam, a cross-sectional beam, which is a rectangle, base B and a depth D. And the formula for bending stress, which is F sub B, is equal to mc over I, where m is the moment, c is the distance from the centroid of the beam to the top base. And for our rectangular beam, c, which is equal to 1/2 of the total depth, or d over 2. And I is the moment of inertia at the neutral axis. And the formula for a rectangular beam for moment of inertia is equal to, or I is equal to, bd cubed over 12. Then you substitute c and I to our formula, which is fb is equals to mc over I, and the summary, f sub b is equal to 6m all over bd squared. And you can change also to f sub b is equals to m over s. And what is s? S is the section modulus, wherein S is equal to bd squared all over 6. So this is a formula for bending stress. For a simply supported beam, typically you need to find using the shear and moment diagram and find the maximum value for moment. And you can use the value for M in this formula. Next, another stress, which is shear stress. And what is shear stress? It is a force tending to cause deformation of a material by slippage along a plane or planes parallel to the imposed stress. The resultant shear is of great importance in nature, being intimately related to the downslope movement of earth materials and to earthquakes. Formula for shearing stress, which is F sub V, is equal to V Q all over IB, wherein V is equal to the shear force, or the maximum vertical shear, while Q is equal to the statical moment of area, and Q is equal to AY, which is area, is equals to BD over 2, which is half of the area of the cross section above, and we will multiply by 1/4 of the distance height. Q is equals to BD squared all over 8. And then I is the moment of inertia at neutral axis, and B is the width at critical shear. You substitute all the formulas to FV is equals to VQ over all over IB, and the shearing stress, or F sub V, is equals to 3V all over 2BD. Example: a simply supported beam 2-inch wide by 4-inch high and 12 feet long is subjected to a concentrated load of 2,000 pounds at a point 3 feet from one of the supports. Determine the maximum fiber stress and the stress in a fiber located 0.5 inch from the top of the beam at midspan. Diagram: we have a simply supported beam, which is we have a hinge at R1 or point 1 and a ruler at point 2, and will cause reaction 2. And we have a 2,000 pounds at a point 3 feet from one of the supports. So in this case, we have 3 feet from point 1, and we have a concentrated load of 2,000 pounds, and the total length of the beam is 12 feet. Let's find first the reaction. So we have the reaction 1 at point 1 and reaction 2 at point 2. Summation of moment at 1 is equal to 0. So we have reaction or the load 2,000 pounds. So 2,000 pounds multiplied by the distance from concentrated load to the moment or at point 1, which is 3 feet. So multiplied by 3 feet, and the direction is clockwise direction, therefore it is positive sign. Another, we have reaction 2. We presume the reaction or the direction of the reaction 2 is upward, so we have a counterclockwise direction from 2.1. So we have negative R2, and the distance from point 2 to point 1 is 12 feet, and equate that to 0. R2 is equal to, so we have 2,000 multiplied by 3, and then we divide by 12, and we have reaction 2. The value for R2 is equivalent to 500 pounds. So this is 500 pounds, and the direction is upward. So we have reaction 2. We need to find the value for reaction 1 using summation of forces along y and equate that to 0. So R1 upward minus 2,000 downward and plus R2, which is 500, and equate that to 0. So R1 is equal to 1,500 pounds. So that's R1, which is 1,500, and R2, which is equivalent to 500 pounds. And then pounds. Let's start with the shear diagram. So first, at point 1, we have a reaction of 1,500 pounds, and it is upward. So in this case, this will be 1,500, and from 1 up to the concentrated load, no load, so therefore it is horizontal line. So from this point up to the concentrated load, and the value is the same at 1,500. From this point, we have 2,000 pounds, and it is downward. So 1,500 minus 2,000 is equivalent to negative 500. Negative 500. And from this point up to the point 2, no load, therefore the curve is, or the line is, horizontal. So from this point up to point 2, and it is straight line. This is equivalent to negative 500. And from this point up to the reaction 2, and the value is 500, and it is upward. So negative 500 up to reaction 2, which is 500, and the value is 0. So this will be 0. And we have the shaded area. Okay, so one, and another one is A2. And then solve for the area 1 and A2 to find the value for moment. So area 1 and the shape is a rectangle, so we have 1500, this one, and the length is 3 feet, so multiplied by 3 feet, and 1500 times 3 is equal to 4500 pounds foot, while area 2 and area 1 is positive, and area 2, it is equivalent to negative 500 times the length, which is 9 feet. The value is negative 4500 pounds foot. So we have area 1, which is 4500 from 0, and the value is 4500 up to the concentrated load. So this will be positive, which is 4500, and the curve or the line is diagonal. So from horizontal line, next is diagonal line. So this will be from 0 up to this point. So this will be 0. From this point, which is 4500, we have area 2, and the area 2 is negative 4500. So 4500 minus 4500, the value is 0 at point 2. And the shape is no load, horizontal, and next is diagonal. From 4500 going to point 2, and the value is 0. And we have closed the moment diagram. So this is shear, and this is the moment diagram. And the maximum moment, maximum M, is equal to positive 4500 pounds foot, and the shaded area, this one. The maximum moment, or M, which is 4500. Maximum So we have the maximum fiber stress, and based on the beam size, we have the base, which is 2-inch, and the depth. So this will be, this is not, this will be depth, which is 4-inch, is 1/2 of the depth, and it is equivalent to 2-inch, and this will be the value for C. So C is equals to 2-inch from the neutral axis to the top of the beam. And the formula for F sub B maximum is equal to MC over I. So we need to find the value for I. And for moment of inertia of a rectangular beam, the formula, standard formula, is BD cubed all over 12. And your B is 2-inch multiplied by the depth, which is 4 cubed all over 12. And we have I. So 2 times 4 times 4 times 4 divide by 12. And we have 10.67 inch to the fourth. F sub B maximum is equal to M, which is 4500, and the unit is pounds foot, and we convert feet to inch, and this is 12 multiplied by 12. So this will be 4500 times 12, or the unit is pounds inch, and multiplied by the C, which is equivalent to 2-inch. We divide by I, which is 10.67. And the value for, or the maximum value for bending stress is equivalent to 4,500 times 12 times 2 and divide by 10.6677 or 67. The value is equivalent to 10,125 and the unit is pound per inch squared. So this is the maximum value for bending. And the stress in a fiber located 0.5 inch from the top of the beam at midspan. So this will be at point, and it is 6 feet from the left side or right side of the support. And in this case, the moment, we will find the moment at midspan. So this is moment at midspan using the ratio and proportion. So let's try from this point downward, and we can have the ratio and proportion of the small triangle and the big triangle. So we have 4,500 divide by the length, which is 9 feet, and equal to the ratio of the small triangle, the height, which is m, the moment at midspan, and divide by at midspan, which means from right support up to this point is half of 12 feet or 6 feet. And the value for m is equal to 4,500 times 6 and divide by 9. And the value for m is equivalent to 3,000 pounds-foot. And we will be using this to find the bending stress at midspan using the formula my over I. So F sub B is equal to my over I. So y for now is the distance from the neutral axis up to the bottom of the 0.5 inch, which is equivalent to 1.5 inch. So this way, so m is 3,000. Same thing, we multiplied by 12 to convert it to inches, and the y, which is equivalent to 1.5, and we divide by the value for I, and the value for I is m bd cube over 12, or 2 times 4 cube all over 12. And we have the value for F sub B at midspan. So this will be at midspan. And the value, so 3,000 times 12 times 1.5, and we divide by 2 and divide by 4 cube, and we multiplied by 12. The value for F sub B at midspan is equivalent to 5,062.5, and the unit is in PSI or pounds square inch. So we have the value for midspan for bending stress, which is 5,600 or 62.5 psi, while the maximum bending stress is equal to 10,125 pounds per square inch or psi. Example: determine the minimum height h of the beam shown if the flexural stress is not to exceed 20 megapascal. So we have the cross-sectional area or the beam size, which is 80 millimeter, and we need to find the height. And we have the beam, we have the uniform load of 2.5 kilonewton per meter and a concentrated load of 5 kilonewton meter, and we have a simply supported beam with R1 and R2. First, we need to find the value for the reaction R1 and R2. Summation of moment at 1 is equal to 0. So we have the uniform load, which is 2.5, and the total length is 1 plus 3 or 4 meters. And then the resultant is at 2 meters halfway, so which means this will be the resultant, and the value from this point up to point 1 is equivalent to 1 meter. So this is equivalent to 1 meter, and the direction is clockwise direction, and it is positive. Next, we have a concentrated load of 5 kilonewton. So we have 5 kilonewton, and the distance from this point up to point 1 is also 1 meter. And the direction is clockwise direction, which is also positive. Next, we have the reaction at point 2 or R2. So we have R2, and the distance from point 2 to point 1 is equivalent to 3 meters. So we multiplied by 3, and the direction is counterclockwise to point 1. So this is negative sign, and equate that to 0. R2 is equivalent to 2.5 times 4 plus 5, and then we divide by 3, and the value for R2 is equivalent to 5 kilonewton. And then summation of forces along Y is equal to 0 to find the value for R1. So we have a uniform load, which is 2.5, and the total length is 4 meters, and the direction is downward, so negative sign, and a concentrated load of 5 kilonewton, and the direction is also downward, so negative 5. The reaction 1, which is upward, so R sub 1, and reaction R2, which is 5 kilonewton, and it is upward direction, so therefore it is plus 5, and equate that to 0. So therefore R sub 1 is negative 2 times 2.5 times 4 is negative 10, minus 5 is negative 15, plus 5 or negative 10. So R1 is equal to 10 kilonewton, and the direction is upward direction, same as R1. R2. So R1 is 10 kilonewton, so this will be 10 kilonewton, and R2 is 5 kilonewton. And we find the value for moment using shear and moment diagram. So first, shear diagram, so 0, and this is for shear, and this is for moment. And first, at point, we have a uniform load of 2.5 up to point 1. So 2.5 times 1 is equivalent to 2.5 kilonewton. So we have negative 2.5. So this will be negative 2.5. And horizontal, next is diagonal line. So from 0 up to negative 2.5, and it is diagonal. Next, from negative 2.5, we have reaction 1 of 10 kilonewton upward. So 10 minus 2.5, and this will be 7.5. And it is positive, so 7.5 kilonewton. And this will be kilonewton. And from 7.5, we have a uniform load up to the concentrated load, and 2.5 times the distance 1 meter, which is also 2.5. So 7.5 and downward minus 2.5, and the value is 5, and it is positive. So this will be 5 kilonewton. From this point, we have a concentrated load of 5 kilonewton downward. So 5 kilonewton minus 5 kilonewton, the value is 0. And by the way, we have the shape horizontal, and next one is diagonal. So 7.5 up to 5 kilonewton, and it is diagonal. Next, so we have the value for, at this point we have 0, and from this point up to point 2 we have a uniform load of 2.5, and the distance is 2. So 2.5 times 2 is equivalent to 5, and 5 kilonewton meter, or 5 kilonewton, and the direction is downward. So this will be 5 and negative 5 kilonewton. Horizontal, the shape is diagonal. From 0 up to negative 5, and it is diagonal. And from point 2 we have negative 5 kilonewton, and the reaction 2 is also 5 kilonewton positive. So 5 minus 5, and the value is 0. So we have the shaded area, and identify that area 1 for the small triangle. So this will be area 1, the trapezoid area 2, and the triangle, which is area 3. And we solve for area 1 up to area 3. So area 1 is a triangle which is 1/2 times base times height, or 1/2 of negative 2.5, and the distance is 1 meter. And the value is negative 2.5 divided by 2 is negative 1.25. The unit is kilonewton meter. Next, area 2. Area 2 is a trapezoid. So the formula is 1/2 times the summation of bases b1 plus b2 and multiplied by height, or 1/2 of 7.5 plus 5 and multiplied by the distance, which is also 1 meter. So 7.5 plus 5 and then divide by 2, the value is 6.25 kilonewton meter. And area 3, which is a triangle, so 1/2 of the height, which is negative 5, and multiplied by the distance, which is 2 meters. And the value is negative 5 times 2 is negative 10 divided by 2, or negative 5 kilonewton meter. From 0, we have area 1, which is negative 1.25, and the value is negative, so this will be negative, so negative 1.25 kilonewton meter, and the shape is horizontal, diagonal, and curve, and it is concave downward. So from 0 up to negative 1.25. Next, from negative 1.25 we have area 2, which is 6.25 positive. So 6.25 minus 1.25, the value is 5, and it is positive. So this is 5 kilonewton meter positive. And the shape horizontal, diagonal, and concave downward. From negative 1.25 up to 5. And last, area 3. So we have area 3 is negative 5, so 5 kilonewton meter minus area 3, which is -5, the value is 0 at point 2. And the shape is horizontal, diagonal, and concave downward. So 5 kilonewton up to 0. And that's it. The maximum moment is equal to 5 kilonewton meter. So this will be the shaded area. And the maximum moment is 5 kilonewton meter. We need to find the value for H using flexural stress formula. So FB is equals to MC over I, and this will be equation 1. So we have the value for FB, which is 20 megapascal, M, which is the maximum moment, or 5 kilonewton meter, and we convert that to Newton millimeter by multiplying 1000 squared, or this will be 5 times 10 to the power 6 Newton millimeter. Next, C, the height H, and the neutral axis for the rectangular is 1/2 up to the top, which is C, and the value is 1/2 of the height, or H. And I, for rectangular beam, the formula for moment of inertia is BD cube all over 12, and the base is 80 millimeter, and the depth is H cube all over 12, and this will be 20 over 3 H cube for I. So we have I, C, M, and F, B. The unknown is H. At 1, FB is 20. Equate that to M, which is 5 times 10 to the power 6, and multiplied by C, which is 1/2 of H, and we divide by I, or 20 over 3 H cube. And we cancel out H, and H, it will be squared. So 5 times 10 to the power 6 cube times 6 times 10 to the power 6 multiplied by 0.5, and we divide by 20 and divide by 20 times 3. We have H squared is equals to 18,750, and we find the value for H. The square root of 18,750 is equivalent to 137 millimeter.